Fox.
Okay, good. All right, so I will present the real-time multi-messenger program of KM3NeT on behalf of many people here. So I will mainly, first introduce a bit on KM3NeT and general motivation for using neutrinos for doing
Feifei,
neutrino analysis. Yes?
can you speak louder?
Okay. Is this my...
Maybe
Sorry,
it's
let me change
not
this.
louder because I don't hear. You look to be very far from your microphone. Yeah.
Hello, can you hear me better now?
Yes, it's perfect. Thank you very much.
Because I hope you can hear me better now. Is the sound fine?
Yes, it's fine. Thank you very much.
Wait, I cannot hear anybody right now. Wait one
now
second.
it works.
Can you hear me?
Yes.
Yes. Okay, good. Okay, now I can hear you too. Okay, great. Okay, I will speak loud also. So, all right. Okay, so I will first mention a bit KM3NeT and why neutrinos are useful in terms of multi-messenger analysis, and I will talk about the KM3NeT real-time framework and the main goals, and finally the alert plans of KM3NeT. So so this is just I'm sure you all already know this. So just to mention a bit, what types of cosmic messenger we have so far on the table. So for example, we have the gamma rays, which I think was discovered a bit over 100 years ago, and they always point back to their sources, but they can be absorbed and also created via different mechanisms. And then we also have cosmic rays. Sorry, I think I missed. But the cosmic rays was discovered about 100 years ago, and they're charged, but they can be deflected by magnetic fields during their travel. And neutrinos, one great benefit of it is that it is neutral and it only interacts weakly, and because of this, it should not be deflected by magnetic fields, and so it always point back to the origins, and can reveal like even if the source is hidden, for example. So there are right now mainly three multi-messenger detections. So the first one is the famous supernova 1987, which you see first around 25 neutrinos were observed before the visual light arrives at the Earth. And then the second one is in 2017, when the gravitational wave detected by LIGO Virgo is combined with the electromagnetic observations by these two satellites, Fermi here and Integra here, and finally, also in 2017, the Blazar TXX0506, which is actually reveals the evidence that Blazar is a high-energy neutrino source. So you can see the neutrino observed by IceCube here, and the coincident gamma rays observed by Fermi and MAGIC. So so this really like opens up the window for doing multi-messenger astronomy, and what's really important or beneficial to do real-time multi-messenger analysis is that because the high-energy neutrino sources are usually time-dependent with the flux quickly varying, so we want to react quickly to them, and providing the accurate positions of the sources are vital for example, redshift or host measurements. And by also doing this simultaneous search, we can achieve simultaneous observations by pointing the instruments very quickly. For example, neutrinos, since they're not bent by magnetic fields, they are excellent tools for pointing the direction of the source for the electromagnetic observatories to do follow-up. And of course, the coincident observations can also help review and determine the nature of a single event, or review even subthreshold events in each experiment. So for example, for this event, a search in the archived IceCube data actually found the earlier flare of these low-energy neutrinos in 2014 to 2015, right? So these neutrinos they were observed, but never really triggered any alert, right? Until later, such coincidence tell us like, okay, these neutrinos are from this source. And of course, to do a full-scale, like complete follow-up is always good to maximize the scientific return of these events. So, okay, I will now turn to KM3NeT. So, since Godfrey already mentioned briefly the KM3NeT detector, I will just skip this. So you have seen this diagram already. So, and we have the ORCA and ARCA detectors. So one is mainly focusing on the low energy part, right? Roughly GeV to a few TeV. And then the ARCA detector is really focusing on the neutrino astronomy in the high energy region, right? TeV to up to 10 PeV, for example. And these are really, ARCA would be really excellent in doing point-like source searches. And of course, both ORCA and ARCA can do the MEV scale core collapse supernova searches. So now I want to mention that the ARCA reconstruction really excellent. So here you see the track in the track channel. This is where we can get the excellent angular resolution. So you see this angular resolution as a function of energy. The red line here is the true neutrino muon angle here. So you see, so this is like the limit we can go, right? And then this this black curve here shows the medium angular resolution. And you can see that we can get a resolution of less than 0.1 degrees at above 100 TeV. So this is a good. And then also for the cascade channel, the resolution is worse, but it's still quite nice. It's around. So here I'm showing you not the most up-to-date resolution, but it's already like less than 2 degrees, and we should have something better than this pretty soon. Okay, now let me mention the current detector status. So for ARCA, we now have 8 DUs, and the full detector would be 230 DUs, and we plan to deploy 50 more next year in April and 12 more in autumn. So the full detector is expected around to finish around 2026. And then for ORCA, we've had 6 DUs from January to November, to just a few days ago, because we deployed 4 more DUs since November 2020. So we have this roughly almost 2 years of ORCA 6 data, and we will deploy more next year too. So, and in total, we should the full detector should be finished around 2025. But with already ORCA 6, you can see on the right the effective area plot. ORCA 6 can already achieve similar effective area as Antares, right? So this ORCA 6 is yellow and Antares is blue. And ARCA 6 is even better than Antares at high energies. So you can see we can already with only like 6 lines. So it's already quite impressive for doing some analysis like similar to Antares. All right, then I will go to the actual real-time alert framework. So this is just a diagram showing the main components of what we can do. So the main, we will have 2 pipelines. One is for the supernova that Godfrey has already described, and then the second one is for the regular neutrino pipeline. So the data would be first triggered and then filtered and reconstructed and classified. And then based on different neutrino selections, and we would have basically two channels for alerts. So the first one is if we see anything interesting ourselves. So these are the self-triggered events. For example, multiplets, which should be the multiple neutrinos coming from the same direction within a short time window, or we see very high energy neutrinos. So these would be already quite interesting to send to external observatories for follow-up. Or the second channel is to we search for any correlated neutrinos based on the external electromagnetic or multi-messenger triggers. And finally, of course, we will send here. This is just to show, okay, what types of reporting channels we have, and the whole speed or the response time is around 10 seconds. So this is let's say nearly real time. And for the actual neutrino alert types, apart from what I just described, so here I there are many two categories, let's say. So the first one is what we've seen usually, the current alerts that we have. So these should be alerts based only on neutrino event properties. For example, the classification scores, or the goodness of the fit, or the energy of the neutrinos. Like for example, you have this signalness parameter, right, from IceCube, which basically tells you the probability of how if a neutrino candidate is from astrophysical origin or not. So this would be an alert stream by the type of triggers, like high energy, or based on the direction, or like for Antares, or something like the bronze or gold alert from IceCube. So here, okay, so for KM3NeT, for Orca, we would mainly issue multiplets, just like I briefly described before, and then also for Arca would be mainly the very high energy events. And the typical alert rate should be around 1 per month.
Feifei,
yes?
just 2 minutes. Well,
2
2 minutes.
Yeah. Okay, okay, yeah, it should be enough. So then for the future alerts, that's what we are currently working now, is to do selection based on astrophysical properties. So the idea is to relax the neutrino alert selection a bit and add cross correlation with astro catalogs and or archived data to do search. So this should be based on the types of sources, so we can maximize the what we can learn in terms of physics. And the alert rate should be around 1 to 2 per month. And here, this is a slide about the alert format. So the video events. So I will skip this since this is mostly technical. So basically, we are ready to send and receive alerts with this format. And the plan for our alert sending is to have a private internal alert ready around spring or summer next year, and the public alert will be around after summer, so October roughly. So okay, now this is my summary slides, so I won't repeat them, but yeah, this is basically what I talked in my slides. Okay, that's it. Thanks.
Okay, thank you very much. For this very complete talk. Is there some question? I have a small one. When KM3NeT will be fully operational? I've missed this or?
Around 2025, 2026, roughly.
Okay.
Yeah, 2-4 years. 2 to 3
Oh,
years,
yes.
roughly.
October 2025. So, wait, not before 2026. Because there will be some delay.
But we will have like, I mean, we deploy the detection units like incrementally, so
yes,
we would be able to do something even like we don't need to wait for the full detector to issue alerts. Yeah.
But is a full detector makes sense? Because I imagine you will have to repair regularly a line. So it's just well.
What do you mean repair?
But do you for maintenance? Do you have a maintenance plan for the lines? Because I know for Antares we're losing some lines regularly. So do you plan to recover the line, to repair them, to deploy them, or?
Unless there is a serious problem, but I don't know. I don't think that's
okay. Damien's answer
needs a
is
regular thing to do. But yeah, maybe Damien can.
Okay,
mention.
if you lose the connection, you let the line on. That's all.
Okay. If we lose connection, I mean, if we lose one DOM, then we leave it, right? But
no.
If we leave like one whole line, I think. I mean, we should be. Well, I don't know what types of reasons is for the.
You can lose Fantais, it happens for okay.
No.
No maintenance is fine. Okay.
I
see just what Damien typed.
So right now, what we have seen for KM3NeT is that once deployed, we have not lost any DOM since 2.5 years now.
Okay.
It could happen that we lose it. Yeah. It's more expensive to replace it, to take it from the sea, refurbish it and deploy again, than build a new line.
Okay, I understand. Fabian, you have a question?
Yeah, I was wondering, you mentioned alerts coming from individual events or these multiplets, which, if I understand you correctly, are also very short-term bursts. But you didn't mention something like the gamma ray follow-up alerts we get from IceCube, the search for accumulation of a neutrino flux over various timescales, coming from ranging from seconds to weeks and months, either for predefined source list or all sky. Do you have something like that in mind as well?
Yes. I think this is more. Okay, I think it would be more on this slide. So to like basically look in historical or like archived, like external like IceCube alerts and or a gravitational wave, and then do actually maybe this is better, and then do cross match with them to see if we have any correlation. So yes, we do plan to do some like long, let's say, like you said, a few weeks or months of archive data search. So not just the multiplex and high energy, like that happens relatively at a quick, fast time scale.
Okay. So Damien also mentioned there's a sliding time window in place, so that would certainly be interesting to learn more how you plan to do that sliding time window and the cross match at the same time. But we can do that offline, I guess.
Michel, you have a question?
Yes, I have a comment on the what you said about cross-matching with data from the CDS in Strasbourg. I like Strasbourg very much myself, but I'm afraid that CDS is not the best place for cross-matching outside stellar data, because as you say, CDS means stellar data center. And by experience, I know they are far from complete for what concerns galaxies and things like that. So you should complement at least with the NED at IPAC in Los Angeles, and perhaps with PanStars and other database. Strasbourg is far from complete for galaxies. Huh?
I see. Okay. Yeah. Good to know. Yeah. Sorry, I'm not. Fully aware of all this, but yes, of course.
I can answer here. CDS means that we will use a tool to do the cross match. It doesn't mean that we only limit it to the catalog which are in the CDS.
Yes, good.
Some very efficient tool to do some cross match with a very large catalog, which has been quite optimized, and that's what we want to use. That doesn't mean that we use only the catalog.
But if the catalogs are not in Strasbourg, you don't reach them, you know.
No, but yeah, I agree. But it's a huge work to do the cross match if we want to do it very efficiently.
Okay, thank you very much, Fefe, once more time. So we're reaching the end of the meeting, yeah? So okay, we switch